about the extrema of function of several variables, section 13.8. Alright, this is not an easy video, so please bear with me. So let's just recall what we have in one dimension when you want to find the local max, local min of a smooth function, right? So the idea is fairly simple. So I have a certain graph. So I have points here and there, right? Where when I go around these points, well, I go down. So this is a local max, whereas here I go up. So this point is a local min, okay? So f of x is bigger than fx0 means that I have a local min. So for all x in the neighborhood of x0, and I have a max if all points in the neighborhood of that point are smaller, the function is smaller than the function at that point. Okay, that's just the definition of max and min. All right, now how do we develop the test? So the key idea is again Taylor expansion, one of the most important objects in calculus. So what's the expansion? Well, so we know that f of x, it's at 0th order, the value of the function x0 plus the linear part, so f prime of x0, x minus x0, so that gives you the approximation of the function as a straight line, and then you go to the next order, the quadratic order, where you pick up that the function is essentially a number, which is given by 1/2 f prime prime of x0, x minus x0 square, okay? And then you can go beyond that and third and fourth and so on if it's the function is smooth enough. Okay, so again, this is the linear part and this is now the quadratic part. Okay, now how can I relate that to the local max, local min? Well, if I want a min, I want f of x around x0 to be always bigger. Okay, so that means that fx minus fx0 is strictly bigger than 0. Well, you see that you have a problem here because x minus x0 can be positive or negative if I'm left or right of x0. Okay, so that wouldn't work to be a local min or local max. Okay, so we ask, because we want that for every x around x0, left or right, we ask that this is equal to 0. Okay, that's x0 being a stationary point or a critical point. So that's the first test, the first criterion. The second one is given by the quadratic term. So now it's good because x minus x0 is squared. So no matter if I'm left or right, I will always be positive. So everything boils down to the sign of the second derivative. And this is what we have, the test for local min, local max that you know. That first of all, I have to decide that if you have a critical point, that is the derivative is 0. And second, I have to decide to look at the second derivative. So here I made a mistake. So that's the second derivative. If it's negative, all right, then f of x will be always smaller than f of x0. Okay, so x0 is a local max. Okay, so another way to see that is in the quadratic term, I'm going to have a parabola, right? A quadratic function in 1D is always a parabola. So if f prime prime is negative, I have parabola going down. Locally, x0 is maximum. And if the parabola is f prime prime is positive, then I have that we have a minimum. Okay? All right. By the way, so if the second derivative is 0, well, what happened is this expansion is 0 and 0 here. So to decide if f of x is bigger or smaller than fx0, I would have to go beyond. Okay, so I cannot decide. So if you look at an example, if I look at x cubed, 0 is a critical point. However, it's not local max or local min. It's an inflection point. And if I have x to the fourth, well, I also have the derivative is 0 at 0, so 0 is a critical point, but clearly I have a local min. Okay, so you need more information in the case that the second derivative is 0. All right, with that in mind, let's go up to multivariate function. Okay, the same idea holds with the Taylor expansion. Okay, and it holds also for not only two input but several input. So remember that we saw that a function, say from Rn to R, I can Taylor expand this. So f at a point V in Rn is f of V0 plus the gradient of f at V0 dot product V minus V0. And remember, this gives you the linear approximation that's related to the tangent plane. Okay, so locally, if I have two input, locally a function looks like a linear function, so it looks like a plane. Okay. All right, and then we would have to go to second order, right? Then you have the same idea that, okay, if I want this V0 to be a minimum, well, locally I want f of V to be bigger than that for any V close to V0, okay? So I have the same problem with that thing because V minus V0, right, it's not necessarily positive or negative. So what we're at, and depends on the direction of V, and so we ask that this is a critical point, which means that the gradient is the zero vector. In other words, that means the tangent plane is horizontal. Okay, so you're either at the top of the mountain or at the bottom of the valley, right? That's being a critical point. Okay, now everything then relies on the second order. So what's the second order of a function? So let's write it for two input because it's not as long. So I have to look at the second derivative. So clearly I should have 1/2 the second derivative in x, okay, times x minus x0 squared, exactly like I have in 1D. Should do the same thing for y, okay? But on top of that, I have two mixed derivatives, okay? So I add the term 1/2 del x del y and del y del x, and now instead of square, it's the product of x minus x0, y minus y0, okay? So that's, by analogy with 1D, putting all the second order derivatives that we know, okay? Now this is long to write, and that would be even longer in more than 2 dimension. So what we do is we use matrix notation, okay? So first of all, you can realize that, well, we know the mixed derivative are equal if the function is smooth, and therefore this boils down to that. These two adds up. Instead of 1/2, I just have 1, okay? And I can rewrite this, we'll just say to you, as a product of a matrix with the vector x minus x0, y minus y0 that I wrote as a column vector, okay? And so if I multiply this matrix with that vector, I get a vector, and then I do the dot product of the same vector with what I had here, okay? So that gives me a number. And if you do the matrix operation, and you should do it, you're going to get the same thing as here, okay? And this matrix has a name, and it's a very important. I want you to notice, I don't think it's in the book, but that's very important. That's called the Hessian matrix at the point x0, y0. Okay, and I'm going to use the notation either H for Hessian or nabla, like the gradient, but with a square, because second order f of x0, y0. Okay? All right. So what do I have then for the Taylor expansion? At second order of a function f, I have f of v0 plus the gradient at v0 dot product v minus v0, and then what we add is the following: 1/2 the vector v minus v0 is doing the dot product with that vector, which is the Hessian matrix times the vector itself. Okay. Now, this seems complicated, but it's just a matrix, and when you do the operation with the vectors, it just sum up to this term, okay? And what is important is that it is a quadratic function of the input, see x squared, y squared, and then you're going to have the mixture of x, y. So this is actually a quadratic function of the input. Okay, and then you could even go further and have the third derivatives and all that, and you would have some error coming there, all right? But for this, determining the local min and the local max, it's all about that matrix, okay? Now, when do I have a minimum? Well, I have a minimum, again, if f of v is always bigger than f of v0 locally. Again, we ask that this is 0 vector, so that's being a critical point. And so to be, for f of v to be always bigger, I would need this guy to be always positive for any v, okay? And that's a property of a matrix called being positive definite, okay? So again, v0 is a minimum if this number that I get is positive for any choice of v around v0, and that has a name for the matrix, the property of the matrix. We say that matrix, the Hessian matrix, is positive definite, okay? And to be a maximum, I want this number to be negative for every vector v close to v0, and that property for the matrix is called being negative definite. Those are two important properties that you will see again if you take the class stochastic calculus with me, okay? All right. Now, if we focus, so being positive definite, negative definite, there's a lot of tests for it. It's related to eigenvalues and eigenvectors. We'll focus on the case 2 by 2 matrix, and then the test is very easy. So if I have a matrix M 2 by 2, say like the Hessian matrix, and I want to know if it's positive definite, well, I need to calculate the determinant, okay? And if the determinant is positive and the first entry is positive as well, then it's positive definite. And if it's negative definite, it's when the determinant is bigger than 0. Also, so it's the same, that's not a mistake, but M11, okay, the first entry is negative, okay? Okay, so to sum up, what's the test to determine local max, local min, or a saddle point is, first of all, you find the critical points, the point where the gradient is 0. Then after that, you look at the Hessian matrix, you compute the second derivative. If it's positive definite, okay, so you compute the determinant and you look at the first entry. If it's positive definite, then it is a minimum, okay. If it's a local max, if it's negative definite, it's a local max, okay? And if the determinant is actually negative, okay, then it's a saddle point. If you get that the determinant is 0, so this matrix is singular, then the test is inconclusive, exactly like when the second derivative is 0 in the one-dimensional case, all right? So let's do two simple examples, but very important, okay? So typical questions that you're going to have is find the critical points and determine if they're local max, saddle, min, or I don't know, okay, using the second derivative test. All right, so let's take the function x squared minus y squared. Then the gradient is easily computed, is 2x minus 2y. So what are the critical points when I want this to be 0 and this to be 0? So that means that 0, 0 is the only critical points, okay? Now, I'm calculating the Hessian matrix at that point 0, 0. So the Hessian matrix, again, is the second derivative in x, second derivative in y, and the mixed derivative in the off diagonal. Okay? So that's easy to do because second derivative in x is 2, in y is minus 2, and you get 0 and 0 for the mixed one. So is 0, 0 local max or local min or saddle? I don't know. Well, in fact, the determinant here is easy, it's minus 4, and the first entry is positive, right? And therefore, if I look at my test, well, actually, I know right away the determinant is negative. That means I have a saddle point. That's not surprising because this is a hyperbolic paraboloid. Okay, so in one direction I go up, in the other I go down, and this is actually what these numbers mean. Actually, this direction I go up, the x direction, the minus direction I go down. So it's a saddle. Now, if instead of hyperbolic paraboloid I have a paraboloid, okay, so I have a plus here. You do the same calculation, and what you're going to get is that 0, 0 is also a critical point. And if I look at the Eschen matrix, then I get 2, 2 now, 0, 0. The determinant is positive. The first entry is positive as well, and therefore I have a local min, which is not surprising because a paraboloid is like, with these coefficients here, that everything is positive, you're going up, and so you have a local min, okay? So those are two important examples because, again, what we're doing here when you do the Taylor expansion is you describe your function f, which might be complicated, but locally, if you zoom in, well, you have a linear part. And if you want a little bit more in terms of approximation, you go to the next order, you pick up quadratic, okay? And so locally, your quadratic functions, they're going to look like quadratic surfaces, okay? But not all quadratic surfaces are functions, okay? So the only one essentially they're going to pick up that are smooth are hyperbolic paraboloid. You're going to have a saddle and a paraboloid up or down, okay? So locally, a function of two inputs, at the quadratic order, they will look like a paraboloid or a hyperbolic paraboloid, exactly like in the 1D case, but it's a bit more complicated here because we have the option of the hyperbolic paraboloid, okay, the saddle point, which we didn't have essentially before. All right? Okay, so I think that's it. Thank you for listening.